All right, so unit circle, right? We went over the unit circle last year, ish. Yeah, ish. Good. Uh, well, kind of. Yeah, not as much as in previous years, but well enough. So you should still be able to put certain trig values together, and this is going to kind of show up all throughout the year. A common vein, trigonometry. So uh, sine of 2 pi thirds. Okay, so if first of all you're like, where I don't even remember what the unit circle is, right? So you could go to my website and Calculus Maximus. If you look up here under Getting Ready Pre-Cal Stuff to know Cold, it's on that one, the top one, but there's also one that's just on the unit circle. But I'll click on that first one. So there's the unit circle, right? You basically, aside from the ones that terminate on the x and y axis, you got your three reference angles, your pi 6, pi fourths, and pi thirds. And as long as you kind of know where it lands, in which quadrant, you can get your signs plus or minus, right? Cosine is the x coordinate, sine is the y coordinate, sine, y, right? And then tangent is y over x, sine over cosine. Cotangent's x over y, cosine over sine. Secant is the reciprocal of which one? Sine or cosine? Secant. Cosine, yeah, good. And then cosecant is the reciprocal of sine. So there you go. This is some of the other stuff we need to know. And again, we'll kind of review this on an as-needed basis. There's a few trig identities over there. Y'all need to know all the way through the power reducing identities, which are on the right-hand side there. So this is a good thing to do your math homework, do your worksheet. This is a good thing to kind of keep coming back to for your own personal enjoyment and reference, you know, because the more often you do it, the more likely you're not going to have to like sit down and just recommit it to memory. It'll just kind of reappear. Oh man, my calculator got too big there. All right, so 2 pi thirds. The reference angle is pi thirds. So again, I'll kind of go through how I do it. Every time I see something pi thirds, I know the ordered pair is 1/2 square root of 3/2, always. 2/3 is just less than 1. Okay, so it's just short of 1 pi. So I'm in quadrant 2. In quadrant 2, I'm left and up. So I know cosine is negative and sine is positive. Oh, it's sine. So it's the y value there, so it's going to be positive square root of 3/2. And that's the answer, positive square root of 3/2. Boom, okay. Number 2, pi fourths, blah, 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 pi fourths. Pi fourths is the easy one, right? Because it's always the same, square root of 2/2, square root of 2/2. 5 fourths, that's just bigger than 1, so we're just past pi in quadrant 3, where it's negative, negative. They're both negative. But it's tangent, right? So tangent's y over x. So it's, they divide out, and you get what type of one? Positive one, yeah, positive 1. 11 pi 6. Pi 6 is your square root of 3/2, comma 1/2. And of course, 11 is in quadrant 4, where it's positive, negative. So you want the cosine, it's the x value there, it's positive square root of 3/2. Just like that. Pi, that's a quadrantal angle. That lands on the axes, that's over at 180. The ordered pair is negative 1, 0. Secant's the reciprocal of cosine. What's the reciprocal of negative 1? Negative 1. Yeah, it is its own reciprocal. Pi thirds, back to kind of the same reference angle as number 1. We're in quadrant 1, so it's just 1/2 square root of 3/2. Cotangent is x over y. So this is the one where your square root of 3, your denominators will divide out. So it can be the numerator of your x, which is 1, over the numerator of your y, which is square root of 3. 1 over the square root of 3. Sometimes, no, did I do that wrong? No, that's right. Oh, yeah. I'm going to talk about rationalizing it. Yeah. In pre-cal, we always rationalize it, but you'll see, like, if it's a multiple choice question, and the answer's there, it may or may not be rationalized. So it's not necessarily something you have to do. And of course, one of the things I'll be saying all year long is if it's a free response question, as long as it's a numeric answer, you don't have to simplify it. So you could leave it like that. But of course, that would also be square root of 3/3. In fact, if you are answering a free response question, cotangent of pi thirds itself is considered a numeric answer. You wouldn't even have to evaluate it. That's kind of weird. Just like e to the third or natural log of 5. Those are considered numeric answers. So I will let you get away with that when we do actual tests in here and it's an actual free response question. You don't have to simplify your numeric answers. So all year long as we go through problems or we learn things, we'll say, okay, here is where we would stop if it were a free response question. But now we have to keep going because we have to train for multiple choice, all right? And then 2 pi, that's coterminal with 0. The order pair is 1, 0. Cosecant the reciprocal of the y. What's the reciprocal of 0? Does not exist, right? Because when you think of 0, it's really 0 over 1. And then when you flip it, it's 1 over 0. So the reciprocal of 0 does not exist is because it's some type of infinity, all right? Infinity and 0 are essentially reciprocals of each other, okay? In the sense that something that approaches something really, really big, its reciprocal is going to approach something really, really small, namely 0. So how are 0 and infinity related? Reciprocals, good. What's the reciprocal of 0? Infinity, because it's D and E because it's infinity. And it could be positive or negative. We'd have to like analyze to see what the sign is. What would be the reciprocal of infinity? 0, good. And that's always 0, okay? All right, that's good. Okay, so the unit circle, y'all seem pretty good on that. Any questions? All right, sufficiently warm? Good warm up? All right. So I'm going to restart number 2 because we didn't. I think I was typing into the calculator and y'all were going out the door. Oh yeah, right. Okay, so let's go ahead and read it. It says if g of x is this, fill in the chart. So again, we have what's called a rational function. In this case, it's a ratio of 2 polynomials. It's a cubic over a linear, and you can look at it right away. And this is one of those habits you want to get into right away. Even really before you read the instructions, it should be one of those automatic reflexes. Analyze the domain. We can't divide by 0. We can't take square roots or even roots of negative numbers, and we can only take logs of positives. We have a denominator here. What value of x is not in the domain? 3, okay? So really, if we were going to be left to our own devices and not told what values to sneak up on, you might be curious about 3, right? It's like, ooh, if 3 is the only value not in the domain, that means that this function's graph lives to the left of 3 and it lives to the right of 3, but not at 3. I wonder what's going on then in the neighborhood of 3, right? Well, that's what the chart's going to lead us to do. So the quickest way to evaluate it, hit play on your calculator, go to y equals. On the emulator, you get the horizontal division bar by doing alpha y equals. Landon informed me if you have the color edition, you can hit math left enter or something like that. Yeah. So here we go. It's going to be x cubed, so that's x caret. You got to use the caret button, 3, and then click to the right, minus 3x squared. And you definitely want to play along and go to the keystrokes all over x minus 3. So I'm really curious if Powell is on board here because the calculator is new entirely. All right. So alpha y equals numerator over denominator. Boom. Now you could type it in. There's your x right there, x. And then your caret is your exponent. Yeah, 3. And then click to the right, the arrow pad. They get you, there you go. And now minus 3x squared. Yes, 3x. There's your x again. Oh, you need to put the x first. So you put your x. Here, we'll put delete. You need x. There's your variable. Now, you could hit squared. That's the only one. Or you could do the caret 2 again. And then click to the right. Either one. Okay, and then you do x minus 3. All right, so again, I don't really care what the graph looks like. I'm just putting this in there as a repository. Now we hit second mode. We quit, right? Second mode, And now we recall it. So the easiest way to recall it is hit the alpha trace. You unlock your F4, and that's the shortcut. You can also hit vars, yvars, function enter. Who wants to do that? It's there at ny1, open up the parentheses, 2.9. Boom. So now I'm just going to type this in, 8.41. Recall it, second enter, put a 9 in, 8.9401, so on and so forth. You forgot how to draw an 8? Oh, you got a weird 8.
I got a weird 8.
Uh-oh. If we had yearbook quotes, that would be a good yearbook quote. I got a weird 8.
I got a weird 8.
I mean, that reminds me of my joke. I don't know a lot of jokes about 8 and infinity, but of course you've heard the one like, what did 0 say to 8? Nice belt, right? But what did 8 say to infinity? Dude, you sleep with your belt on? I made that one up. Right. Yeah, thanks. So if you notice, you're going to get the same values as you did up above. Okay. This time for me, it was by design. So it's not the same function, obviously. One's F and one's G. They look very different, but we have the same value. So if we answer the questions, what do these values tell us about G in the neighborhood of 3? Yeah, I mean, it's really the same thing as up above. We could say as X approaches 3. Yeah, from both sides. As X approaches 3, from both sides again, comma, G, or you could say Y, either one, they're interchangeable in this case, G approaches 9. Yeah. The same thing's happening here in the neighborhood of 3 as was on our old friend X squared. Now, again, if you're just a mathematician detective and you don't know the equation that generated these values, is there evidence that would tell you what G of 3 actually is? Well, you might say the same thing, right? You might say 9, but being a good math detective, you're also, after the first experience, saying, you know what? Just because the roads from both sides are leading to 9, does that mean that there's a bridge in place at 9? No. I wouldn't want to be driving with you if you're assuming that, unless you're Bo or Luke Duke, right? Duke's a hazard, yeah. So not really. And the whole point that we're trying to make here is the limits in the function value, which is G of 3, they can exist entirely independently of each other. So what is G of 3? We actually know G of 3 is what? It does not exist. We knew that from the very beginning, okay? We knew that from the very beginning. Now, just to review from pre-cal, if it's a rational function like this, anything that makes the denominator 0 is for sure going to be a discontinuity, but it's going to be a whole or a vertical asymptote, okay? We know that this one has to be a whole based upon our numerical evidence, right? Because we're approaching 9 from the left and approaching 9 from the right. And if it were a vertical asymptote, as we got closer and closer to 3, what would happen to the y values? They would go up hugely fast towards either infinity or negative infinity. And that's why a vertical asymptote is also called an infinite asymptote. But remember, there was also a way to determine that by plugging in. So the 3 makes the denominator 0. What do you get when you plug a 3 into the top? 27 minus 27, right? 27 minus 27 is what? 0. So remember, 0 over 0 means that there's a whole, and non-zero over 0 means that there's a vertical asymptote, okay? 99 times out of 100. There's like one time where 0 over 0 actually means jump, but we'll meet him later. His name is Hombre Trepador, right? Or Senor Salta when he made a guest appearance on Dora the Explorer. Yeah, okay. So cool. So is there a mathematical way to communicate from above? Yeah, there absolutely is. And again, we'll write it like this. The limit, LIM, as x approaches 3 from the left of g of x now. So just like function notation, we have the input and the output. But instead of just saying g of 3, we have the g up here, and then we have the 3 down below. It was 9. And then I'm going to go ahead and say g of 3 equal dne. And then over here, I'll put the limit as x approaches 3 from the right of g also equaled 9. So it's so important now to have this idea of the limit, especially, I guess in this case, when the function doesn't exist at a place, because it still gives us a way to communicate what's happening in the neighborhood of. But when they all three do exist and they're all the same, it gives us a way to talk about being able to drive across safely, which is important to the idea of continuity. So what we're going to be able to do here shortly is define every single discontinuity in terms of a limit definition, okay? And similarly, not only can we collect data and write it like this, but if you're given this type of information, you should be able to determine what type of discontinuity it is, right? It goes both ways. If you know the road coming in from the left and the road going out on the right, both go to 9, but the function value doesn't exist, you know it's got to be a hole. It's going to be a removable point discontinuity. Do your worksheet. The bridge is out, right? And there's the picture of it, okay? To say what we just did here, this would be like x equals 3. And the road coming in from the left was approaching y equals 9. And the road going out on the right was also at y equals 9, but the bridge was out, okay? And we have a hole. We have a hole, okay? Now, the reason it's called a hole is because it's an open circle, but it's connected on both sides. You can have open circles that are parts of jumps that are not considered holes. So the real name, again, is a removable point discontinuity. It's the only type that we're going to study that's a removable. What makes it a removable discontinuity? Well, imagine that it was intact and someone literally came and just removed one point. They swiped it away. Swipe or no swiping, right? They removed a single point. If we were to find Swiper and beat him up and get that point back, we would know now exactly where to put it to make it continuous again and safe to travel across. We would put it at the point 39. So that makes it a removable point. And of course, for obvious reasons, it's a discontinuity. The other two types of discontinuities that we've talked about that we're going to define shortly, the vertical asymptote is non-removable. Beat up Swiper all you want, you're not going to be able to make those roads connect. Even if they both go up to infinity, can't make them connect. And then, of course, the jump. Not going to be able to make them connect. But you can still beat up Swiper. Okay? He never got beat up on those shows, which is probably a good thing, because it was a kid's show. It was. Yeah. You just made him out to be a villain. And, you know, you stereotype foxes as bad people. You know, I don't know. That's right. Like on Blue's Clues when Steve went to college. Yeah. Yeah. That pretty much ended the show for me. Yeah. Sorry. All right. Okay, so we did answer this part A from the equation of the function above. How can we algebraically determine that the function had a hole at that value? And again, we could just say g of 3 not only equal dne, but it was 0 over 0. Okay, that's how we know it's a hole, 0 over 0. If you were to build the bridge and fill the hole, at what value? Well, we would fill it in. You fill in the hole at the point 3 comma 9, right? Which ends up being the same as 3 comma the limit as x goes to 3 of g of x. Now notice what I didn't put here for the first time. I didn't put plus or minus, and that's going to lead into a theory that we're about to have. If you don't see the plus or minus there and you're approaching a finite value of x, not like infinity or negative infinity, then this is what I call the general limit. It's a two-sided limit, okay? And it only exists if they're approaching the same thing. So we found the y value of the whole in pre-cal before we even knew that it was the idea of a limit. But this gives us kind of connection. If you ever want to know what the y value of the whole is, it's the same as finding the limit. Well, let's flip that on its head. If you ever want to find the limit algebraically at a place where you know there's a whole, we could do it the same way as finding the y value of the whole, which if you remember how we did that in pre-cal, well, I'll show you. It's example 4, okay? We're going to go ahead and find algebraically the coordinate of the whole, okay? In other words, we're going to algebraically find the limit, the general limit as x goes to 3, okay? Here's how we're going to do it. We know 3 is not in the domain, so let's write this again. Connections, connections, everywhere connections. We do get 0 over 0. It's a polynomial over a polynomial. So if we go way back to like algebra 2, I think there was something called the root theorem or the factor theorem, which basically says in a polynomial, it says this, very important. If x equals a is a root, and root is the same thing as a 0, okay? In other words, f of a equals 0. That's what it means, okay? Then x minus a is a factor. And it works in reverse and vice versa. This is actually an if and only if statement. If and only if statements, they work both ways. You can put an if, then, and then you can flip it around, if, then. They work both ways. It's more like a definition or a postulate, okay? So if you know a root, you know a factor, and if you know a factor, you know a root, right? So if I had a polynomial and I plugged in a 3 and it gave me a 0, I know it's a root, then I know x minus 3 is a factor. Beautiful. If x minus 3 is a factor, then I know x equals 3 is the root. Now that one we're used to seeing because that's the zero product property. When you factor and you set them each equal to 0, you can find the root, but it works the other way around. So look at the consequence. If I plugged in a 3 and I got a 0 over 0, I know then that on g of x, I could factor the top as x minus 3 times something, and I can factor the bottom as x minus 3 times something. Yes, yes? Yeah. Cool. Well, once you have it factored, guess what happens to the x minus 3s? Very good. Yeah, if you've had me before, we know those don't cancel. We had that conversation in pre-cal today. They divide out. Things divide out to give you 1. Things cancel to give you 0. And so once we get rid of that problem area, we're going to be left with a function that is the same everywhere except at, in this case, 3, where the remaining function paves right over it. So the y value of what's left essentially gives us the y value of the whole, which we know now is going to be the limit value that we're interested in. So let's go ahead and do that. And I'm going to go ahead and set it up this way. I know I want to find the y value of the whole, but I want to start thinking that now as the limit. So I'm going to put the limit as x goes to 3 of g of x, but I'm going to write g of x in there. Okay? I want to evaluate this limit. I don't have a calculator at my disposal. I can't type in 2.99999 and 3.00001. It's too tedious without a calculator. I don't have one. So if I try direct substitution, I'll see that I get 0 over 0. And you're like, oh, there's a hole at 3. Do your worksheet. let's just factor out the x minus 3, okay? And to do that, let's see. The first rule of factoring is to look for a common factor, right? That's the first rule of factoring, the GCF. So in the top, what's the common factor? X squared. We'll factor that out, and we're left with x minus 3. And on the bottom, there's just an x minus 3. Now, notice the x minus 3's divide out. If I leave it like this, I don't need to put parentheses around x minus 3. But when I divide it out, because I want to show that I'm taking the entire quantity x minus 3, I'm going to put it in parentheses. And then those divide out. Now, remember when we got the same numbers in the tables in number 1 and number 2? Now it's obvious why that happened. G of x on number 2 and f of x from number 1 were exactly the same. It's just the graph of x squared, except on number 1, it paves right through the point 3, 9, and on g of x, there's a hole at 3, 9. But this is why it works. If I can find the y value of x squared at 3, that's the y value of the hole. So in pre-cal, we just memorized factor, divide out, and then plug it into what's left, right? So once this is gone, 3 squared is 9. And that's how we get 9. So this is going to be summarized in 1.4. When you're trying to evaluate a limit, plug in first. If you get 0 over 0, and it's a polynomial over a polynomial, factor, divide out, and then plug into what's left. And when you plug in, you don't need to write the limit anymore, because remember, we're working with expressions. And when you work with expressions, you don't need equal signs. You're just basically saying this equals this, which equals this. So we're saying the limit is 9. Now, let's go ahead and formalize what it means to have the limit without the plus or minus. Oh, and if you want to write this, you could say, so G has a hole at 3, 9. Really? It means the same thing, right? Interchangeable, just two different ways to look at it. So here's the definition of the general limit. And it's an if and only if. So the way we list if and only ifs, and I'm trying to do the notes differently here. The theorems and the definitions I'm putting in green, okay? So here's your double-headed arrow. That means it works both ways. So let's start by putting an if on the left. If the limit as you approach some x value, call it c, from the left of a function is L, which happens to also be the limit as you approach that same x value from the right of the same function. In other words, if the limit from the left equals the limit from the right. In other words, if the road coming in from the left is pointing towards the road coming in from the right. You don't even look at the bridge, right? If the roads are lining up, then we say that the general limit exists and it's equal to that same y value, okay? If the roads are pointing towards each other, who cares if there's a bridge or not, the general limit exists and it is that y value. And then it works the other way around. If we know that the general limit exists and is 9 in the case above, then we know that the roads are pointing at each other from both sides. Does this limit theorem tell us anything about whether or not the function value exists or whether or not we can drive across safely? No. This is just concerned with the limit, okay? Just with the roads. This is the roads only. Roads only. Okay, so if you know the general limit, you know both the left and the right. But if you only know the left limit, you don't really know the general limit, okay? So what would be the converse of this? Let's say that the limit from the left exists and the limit from the right exists, but they're not the same. Will the general limit exist? No, it won't, okay? What if the limit from the left exists, but the limit from the right doesn't even exist? Will the general limit exist? No. Okay? So there's lots of ways where the general limit can fail to exist. Okay, if the two limits exist but are different, the general limit won't exist. What would that look like if the two one-sided limits existed but were different? That'd be a jump. Very good. What would it look like if one or both possibly limits from either side did not exist? Vertical asymptote. Yeah, good, good. So you can see where this is all heading. All right. So now example 5. We've kind of looked at examples prior to this to try and tie connections together. And now we kind of have a fresh function. Don't really know what it looks like graphically, but we do know it's another rational function. It's a quadratic over a quadratic. It says to algebraically determine the following. Okay, letter A, f of -1. Is that a calculus question? F of -1? No. Is that the same thing as finding the limit? No, this goes back to algebra 1. F of -1 is, what is the y value at -1 if it exists? If it exists. Is there an ordered pair you can go stand at? Well, it doesn't say to use a calculator, but you can. I'm gonna not use one. Let's use direct substitution. Plug it in the top. -1 squared is 1. This becomes -4. 1 minus 4 is -3. -3 plus 3 is 0. So I'm going to come down here. Right below there, I'm going to put 0 in the top. Now, just because I get a 0 in the top, does that mean it's going to be 0 in the bottom? No. No. Okay. Does that mean DNE automatically if I get a 0 in the top? No. Okay. So let's plug a -1 in the bottom. -1 squared is 1. This becomes plus 3. 1 plus 3 is 4. 4 minus 4 is 0. Okay. Now, because I get a 0 in the bottom, I know the function value does not exist. There is no bridge. Okay. So now I can't leave it as 0 over 0. I have to say DNE. The DNE is entirely because of the denominator 0, not the top. Okay, does that make sense? But do your worksheet. Because I also got a 0 in the top, as well as the bottom, I now know what that function has at -1, right? A what? A whole. So does the general limit exist for this function at -1? Yes. Yeah. Does the limit from the left exist at -1? Yeah. Yeah. Does the limit from the right exist at -1? Yeah. Function value doesn't. Okay. The roads are pointing at each other. Good. 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 So here you go. Find the limit as x goes to -1. Well, look what C and D are. If I answer the question to B first, doesn't that pretty much give me the answers to C and D? Yes. Yes. So now, how can I algebraically, without a calculator, find that general limit? Factor, divide out, and then plug in. Yeah. Okay. So I'm going to go ahead and keep it all down here. So because I've already plugged in a -1 and I got a 0, that means -1 is a root of both the top polynomial and the bottom polynomial. Therefore, what do I know the corresponding factor is? X plus 1. Very good. So here's what I'm going to go ahead and do. I'm going to go ahead and just write this, the limit as x goes to -1. And I know, if you want, let's go ahead and write that in there first. X squared plus 4x plus 3, x squared minus 3x minus 4. Okay. There are a couple ways to do this. You could just factor it up above without the limit in front, but I want to go ahead and set the problem up. Now, notice again how I'm doing this. I'm working straight down with no equal signs. Some people want to do this. They want to put the limit as x goes to -1 equals that. Does that really make sense? No. You always have to have the limit of something behind it. You don't say the limit with nothing and then equals that. That's not true. All right, so now I can go ahead and factor. Now, I probably don't even need to know that x plus 1 is a factor of the top and bottom to factor the top and bottom, because we're accustomed to factoring these relatively nice quadratic trinomials when the leading coefficient is 1, right?
Yes.
But might as well let it help us. There's no common factors to pull out. There's no common factors to pull out. So I know the top is going to be x plus 1 times, and let's say that you're a little bit rusty on your factoring. You can use that to help you force it then. It has to be an x in the front, and then to get a +3 with a +1, it has to be a +3. And then if you check the inner and outer, you get a +1x, +3x, you get +4x, boom. And in the bottom, it's got to be an x -4. Okay. Now there will be times where you might need to know that x plus 1 is a factor, and it can help you factor or get the other factor because you'll have to divide it out. All right, so now that we have the limit in front and we have the expression, you can divide it out, and now you go back to direct substitution. All right, and when you plug in, after you divide out, when you come back and plug in this -1 into this residual function, that's when you don't need to write the limit anymore. So -1 plus 3 is 2. -1 minus 4 is -5. Okay, so here is kind of the rule. When you set up a limit, as long as you still have variables, you need the limit in front. But as soon as you plug in, that's when you don't need the limit. There you go. So if you had left this limit off and it was a free response, you would lose a point right there. So always double check, come back, and if you have variables still, put the limit back in front. You can fix it on the back end before you turn in your paper. But it's helpful if you kind of keep it in front as you go, because you're reinforcing what you're doing. So again, here's what we've said. This is an expression. There's no equation here. We're saying the limit as x goes to -1 of f of x is -2/5. And there's the work that supports it. Okay? Well, now by the limit theorem, if we know the general limit, then we know this is -2/5. And we know that this is -2/5. Now notice how I wrote the -2/5 each of the 3 times. I put the negative in a different place. Are those all equivalent?
Yes.
Yeah. If you just have a single numerator and a single denominator, in other words, not multiple terms, then the negative could be associated either in the bottom, the top, or it can be pulled right out front on the same level as the horizontal division bar. Okay. So again, very important. If I know the general limit, I know both one-sided limits. But if I only know one of the one-sided limits, I don't know the general limit yet. Okay. Part E, based upon our answers above, what type of discontinuity does the function have? And what's the coordinate? Okay, so let's see. If the general limit exists and we're going to lunch and the function value doesn't, what do we say here? As you're going to lunch? Very good. We're going to improve upon that after lunch because we don't want to say there is. We want to say instead F has. A little bit more specific. Have a great lunch. Go nourish your body, and we'll see you when you get back. Good. All right, we're back on. So before I answer part E, let's come back and address a question that was asked as people were going to lunch. So when I set up part B, you know, I set it up with the limit in front of the function, then I factored. But if this were truly the question, you could actually, you know, let me borrow this line here. Well, let me just borrow this line. You want to be careful that you're not being too casual with your work, and whenever you're equating two things, you better make sure that they're actually equal. So if you want to go ahead and factor up there without putting the limit in front, that's fine. And then the x plus ones divide out. But then here's what you want to be careful. If you're answering part B, you don't want to just keep this going down here and say that that equals negative 2/5. Okay? So why is that not true? Is f of x equal to negative 2/5 always, every time? No, that would be a horizontal line. No, f of x is equal to the line above. When is it equal to negative 2/5? It's only equal to negative 2/5 as we approach -1, okay? But you could then, if you did have it factored up there, then you wouldn't really even need to have this stuff, and that's what Ethan was asking. So you could just get rid of that because it is factored above, and then you're plugging in, and then you could just have this here. And again, if you work straight down, you don't need the equal signs. If you already know the answer and you want, you could just work left to right and say it's negative 2/5. That would be fine as well. Okay? So little differences like that, still equivalent. Just be very mindful of your notation and equating things. Okay? So now, based on the answers above, what type of discontinuity do we have? It says to justify. So we know there's a what there? A hole. Now, if it does say to justify, we've kind of talked about it. We haven't formally defined it, but it's because the general limit exists, but the function value doesn't, right? In this case. Or you can break it up and say because of C and D, the limit from the left equals the limit from the right, but they don't equal the function value. So I'm not going to write out that sentence yet because we haven't defined it, but that's what we're getting to down here. But let's go ahead and just at least answer the second part of that. We'll say then that the function's name is f. Okay, so we'll say f has a, yeah, and you can refer to it as a whole. That's fine. You don't have to write out removable point discontinuity. And that goes for the AP exam as well. F has a hole at the point and -1, comma, -2/5. Okay. And if you had to justify, you could say it would be comma because. We'll go ahead and try it. The most concise way would be because the limit as x goes to -1 of f of x equals -2/5, but f of -2/5 equals dne. Okay? That would be the justification. Now, could we have a hole at a location and still have the function value existing? Or does it have to be dne? It can still exist, but if it does exist, it's not the same as the limit, right? In other words, as long as the roads are lining up but not connected, you're going to have a hole. It doesn't matter if there is no bridge or if the bridge exists but it's built somewhere else. Silly construction people, right? Okay, so that gets down to here. If our goal, and that's where this is leading, the idea of continuity. Did I write something wrong? People say. Oh, yeah. That's okay. Good, yeah. That is supposed to be -1. Good catch. Good catch. Yep, that happens, yeah. Careless mistakes. And this is why I don't want cell phones out. This is why I don't want like earbuds out, because I was already thinking about what I was going to say next. And yeah, and if you break your concentration, you can make careless mistakes. We don't want that. So if I made this image myself, I know you're impressed, right? But if our goal is to safely and smoothly drive across a canyon or a gorge, we need to establish then what relationship between the two one-sided limits and the function value need to be at that particular x value. And I think it's pretty obvious, right? If, bless you, we want to drive across safely, the limit from the left has to equal the function value, which is the bridge, which has to equal the limit from the right. They all have to exist, and they all have to be the same, right? And that's it. If any one of those three things either fails to exist, or if any two of them don't equal each other when they do exist, we're not driving across safely, right? This brings us then to one of the most important parts of this section, the three-step definition of continuity at a point, okay? And when we say continuity at a point, we can either mean that to be at the x value, or because it'll be continuous, it could be the ordered pair, all right? So let's talk about it. A function f now is defined to be continuous at a point x equals c. No longer the informal definition, which was if you could draw it from left to right through that point without lifting your pen or pencil. No, we now have a rigid, more formal definition. If, okay, the limit from the left equals f of c, which equals the limit from the right, okay? And the reason that I like it like this is because it does kind of keep that analogy of driving in, across, and out. The road in equals the bridge equals the road out. And when we say that the road in equals bridge equals road out, we mean the y value, right? We mean the vertical location. All right, so that's why I call it the three-step definition. Real intuitive, real easy to remember. But you could also do this, right? Or if you want, you could say the limit as x goes to c of f of x equals f of c, right? That accomplishes the same thing, doesn't it? Because the left part, the general limit, takes into consideration the two one-sided limits. I don't like that one as much because I can't imagine like driving across that way, because I can't drive across the in-road and the out-road at the same time, right? So I think it's easier for students to remember, you know, drive in, drive across, drive out. All right, so notes on justification, because you're going to be asked to justify whether or not a function is continuous at a location. So you're going to have to collect your data. So as we work the problem, I will show you. We set up the notation first, because right now the notation is kind of new, and then we go out and collect our data. And once again, if any one of the three fails to exist, it's not going to be continuous. You need a road, you need a bridge, you need a road. Anyone's missing, it's not going to work. But it could be that they all three exist, and it could be that they're all three of them are different values. Whoa, what a botched construction project, right? Okay, so don't get confused on number 4. Don't get confused with the limit definition, which are the roads only, right? If the limit from the left equals the limit from the right, the general limit exists. Don't get that confused with the three-step definition of continuity. It happens invariably that I ask someone to tell me if a function is continuous at a point, and they'll say the limit from the left is 5, the limit from the right is 5, therefore the general limit is 5, and the function's continuous at 5. And I'm like, did you ever consider the bridge, right? Because they're in their mind, they're considering 3 things, right? But they're not really. They're considering 2 things and then the conclusion, okay, for those 2 things. So a road is not a bridge, nor is a bridge a road, okay, in this sense, right? Okay, so we can now formally define the removable point discontinuity, all right? If for some function at x equals c, if the general limit exists, call it L, but either the function value there is undefined, no bridge at all, or the bridge does exist, but it's not L, right? Then the function f has a removable point discontinuity at c comma L. And then it works the other way around. So basically, there's only two ways you're going to be able to draw it. It's either going to be like this. Okay, we'll call this x equals c. And then this right here would be y equals L. Or it could be something like this. We'll say this is x equals c. We can have y equals L here. And then maybe you have, something that looks like that. So in the top one, the function's not even defined at c. In the bottom one, it is defined at c, but it's either above or below the hole. Okay? In both cases, we say that the hole is at c comma L. All right? The hole is always at c comma L. All right. Now, both of those are considered removable point discontinuities because all you have to do is plug the hole to make it continuous. In the bottom one, you could think about it as just like relocating the hole to make it continuous. In the top one, you have to beat up Swiper to get that hole back first, or the bridge back. Right? If you don't think Swiper can actually steal a whole bridge, you could think of it as like a manhole cover if you want to think about that. Kind of the same idea, right? So there you go. There you go. That's the removable point discontinuity. Let's try it out. Example 6. Ready? Example 6. We're in here till 1:35. Using the three-step definition of continuity. Okay? Road in, bridge, road out. Determine whether or not the graph of the following function h of x is continuous at the following x values justify. So again, the justification is going to be, do any one of the three fail to exist? Do any two of them not equal each other? Or, hey, if they all exist and they all equal each other, let's drive across. If it's not continuous at the indicated value, name the type. Okay, got it. Step 1, h of x is a rational function, right? It's a cubic polynomial over a quadratic polynomial. There could be up to 2 values of x then that make the denominator 0. So there could be up to 2 discontinuities. They could be both vertical asymptotes, both holes, or you could have one of each, or it could be that the domain is all real numbers, right? Just because you have variables in the denominator doesn't mean values of that might make it 0. All right. So now we're going to use the three-step definition at x equals 2. Would it be helpful, and this kind of gets back into what Ethan was doing, would it be helpful to factor that thing one time off to the side and then use the factored version? Yeah, it might. It might. So let's go ahead and do that. You have that option. So let's go ahead and do that. And you can do that in part A. It's going to have to get factored eventually. So might as well factor it without the limit in front because it's less work. So here we go. In the top, if I factor out an x, I'm left with x squared minus 4. And then in the bottom, let's see, factors of negative 20 that add up to 8. So how about x plus 10? Yeah. X minus 2. I like that. Oh, no. Can you go straight to x minus 2, x plus 2? Yeah, absolutely. Yeah. If you know you're going to pull an x out in the top and you're left with x squared minus 4, you can go ahead and go straight to that. Yes. I usually don't do that when I'm instructing or when I'm not, because I make careless mistakes really, really well. Okay, so there it is. It's completely factored. So now, even if we didn't know what the question was asking us, we could probably anticipate what it might ask us because we kind of know the behavior of this thing. We know that there's two values of x that are not in the domain. What are they? -10 and +2. Yeah. So remember that you can determine if those two discontinuities, -10 and 2, are wholes or vertical asymptotes by plugging them into the top. 0 over 0 is a whole, non-zero over 0 is a vertical asymptote. But if you already have it factored, you don't really need to plug it in, right? Because look at this. If it causes a 0 in the top and the bottom, it's because that factor is in the top and the bottom. And that's going to give you the 0 over 0, which would make it a whole. What's the other proper name for a whole? A removable point discontinuity. What was I just able to do with the x minus 2 factors? Remove, yeah, I factored and divided them out, but I removed them from the equation, right? So there's that symmetry there, or the parallelness. If you can remove the factors from the equation, it's a removable point discontinuity. So it's just the other way to determine it. Either 0 over 0, or you can factor and divide them both out. The x plus 10, I can't remove it from the equation, right? It's stuck there. Guess what the formal name for a vertical asymptote is? It's a non-removable infinite discontinuity, right? So right away I know that this function has a whole at x equals 2 and a vertical asymptote at x equals -10. And if I wanted to know the y value of the whole at 2, I could just plug a 2 into everything that's not divided out. All right, so let's answer the question then. Is this function continuous at 2? No, okay? So in a complete sentence, no, comma, h or h of x is not continuous at x equals 2, comma, because, would we say because it's got a hole there? No, because that's not based on the three-step definition. The three-step definition is, again, if they all three exist in the same, it's continuous. If any two are not equal, it's game over, or if any one of them fails to exist, it's game over. And then depending on how it fails, that would then tell you what type of discontinuity it is, all right? So what would be the easiest? Does the general limit exist at 2? Yes. Yeah, so the limit from the left will equal the limit from the right. But what doesn't exist at 2? H of 2, the bridge, right? So that's all you have to say. No, H is not continuous at x equals 2 because H of 2, you could either write out does not exist, or you could put equals DNE, which I don't know if I've said it yet, but of course DNE stands for does not exist. Yeah, boom. Okay. So that would be, you know, if you already had it factored. Here's another way to do it. I'll just say or, and this is kind of another way that I like to do it. If I need to determine if it's continuous at 2 or not, this is where I'm going to, what I said earlier, set up my notation. So I would say, what would be the limit as x approaches 2 from the left of h of x? What is h of 2? And what is the limit as x goes to 2 from the right of h of x? Okay? And when you write it like that, you make columns for the work. So your first column is the road in, second column is the bridge, third column is the road out, right? Now, any one of these, let's see, what would be the limit from the left? Well, this is where you go off to the side and factor. Just for kicks and giggles, let's figure that out. If I plugged a 2 in to everything that's left, I'm going to get a 2 times 2 plus 2 all over a 2 plus 10. Can I call that h of 2 since I'm plugging a 2 in? No, I better not call that h of 2. So what could I call it instead? I would probably say, I would just say, you always want, I would say plug in x equals 2. I would do that, maybe. Plug in x equals 2. And what does that give us? It gives us 8 over 12, which simplifies to 2 over 3. Okay. So, yeah.
I was gonna ask you,
Go ahead.
do you have to like put the equal sign in front of it, or can you just like leave it with that one? Or do we need to like tell you we're plugging it in here?
Oh, yeah, you need to. Yeah, you need to. Because if you just have variables and then on the next line it switches to numbers, remember when you're working straight down, you're saying they're equal. And they're not equal, right? A variable function does not equal a constant. It only equals a constant when you plug a number in. So you would need to show that notation. Yeah. Yeah. Yeah, you can't put h of 2 because h of 2 doesn't exist, right? H of 2 is DNE. But you could put the limit in front, right? Right. So that's what I'm doing over here. This is 2/3. This is 2/3, right? Or it could be, look, it could be this. It could be that you don't even label that. But then when you plug in your 2, you don't want to do it right below there. Because when you work below, it's considered sequential. So just move it off to the side like that, right? And now it's kind of like its own separate thing. And then, of course, h of 2 would be DNE. And that would be kind of like doing it by checklist, right? Every time. What's the limit from the left? What's the bridge? What's the limit from the right? Collect your information, make your claim. But you don't have to do that. If you factored it first and you realize the function doesn't exist, so there's no way it's going to be continuous, you don't have to find the limit there just to say it's not continuous, unless it specifically asks for the limit, okay? Now, it's kind of good to know if we were eventually trying to sketch this graph, man, I would know to put a hole at the point 2, 2/3, right? Cool. All right, letter B, is the function continuous at 0? Yeah, if we use our pre-cal knowledge, right, the only place where this function is not continuous is at -10, where we know there's a vertical asymptote, and at 2, where we know there's a hole. So we know it's continuous at 0. How do we justify it? Do we just say, yep, because 0 ain't 2 or -10? Yeah, what did you say? You have to? Yeah, you just show that they're equal, right? So we'll just say yes, yes, H, not his, H is continuous at x equals 2, comma, because, and now you could do it all in one step, right? You could say yes, because the limit, yeah, it's 0, sorry, thank you. Because the limit as x goes to 0 from the left of h equals h of 0, which equals the limit as x goes to 0 from the right of h. Now that's the bare minimum. What's kind of, if you write it like that, it's correct. You'll get full credit, right? That's just the 3-step definition. But if I left it like that, I would walk around the rest of the day with that unresolved feeling in my sinuses like I have to sneeze, but I didn't, because what am I missing there that would really help me feel better? What the actual value is. It's not critical for the argument because you have the notation written out beautifully. So if you want to, you could just put like an equals there, and then what do you get when you plug in a 0? You can plug it into any version you have. It's probably easier in the very first one, right? The expanded version. You get 0 over negative 20, which is what? 0, right? You get 0 over negative 20, which is 0. Okay, so that's an optional thing. But again, if we're trying to sketch the graph of this dude, I know this function is continuous at the origin, right? At the origin. So real quickly here, 0, we'll just summarize again. 0 over 0 means whole. Non-zero over 0 means vertical asymptote. And 0 over non-zero is what? 0. Yeah. Yeah. There we go. So it's only when you get a 0 in the denominator that it's a discontinuity. Okay. All right, and then I think we have time for one more here. Negative 10. Well, we know that it's not, right? Yeah, so do we say no, H is not continuous? Continuous at x equals negative 10, because the justification is not because, yeah, you could use any one of the three. None of them are going to exist. Now, you got to be careful if you say that the limit from the left is positive infinity or negative infinity. You have to know which one it is, right? And so that would require a little bit of analysis. You could say D and E, because here's the deal. A limit can fail to exist for a whole bunch of different reasons. D and E becomes kind of a catch-all. A limit can fail to exist because they're approaching two different things from either side. It could be because they're increasing without bound, like towards infinity. What would still be the easiest reason? Yeah, H of negative 10 doesn't exist either, just like on A, because H of negative 10 equals D and E. Okay, or you could say because the limit as x approaches negative 10 of H of x. I wouldn't say infinity, I wouldn't say negative infinity, and I wouldn't say plus or minus infinity. I would just say D and E as well. We'll get to a whole section where we're analyzing what type of infinity it is, okay? Because you are expected to know at a vertical asymptote from one side if it's positive or negative infinity. And you want better odds than 50-50. So it's not a difficult thing to do. So that's probably the easiest way to do it. And then back to what you said right before lunch. You don't want to say there is a vertical asymptote. You want to say H has a vertical asymptote at x equals negative 10. Always be very specific, okay? All right. So got a lot of theory in. We should be able to finish these notes tomorrow, believe it or not. We should, okay? We got discontinuities and then a real quick thing. So be working on that worksheet to 1.1. It's on my website. It's also in Canvas, and the key is posted. So check your work. We'll probably quiz on Friday for the first time, okay?
So, Mr. Coffee, would it matter if it's the general limit or